Okay, so you just turned in, what was it, what was the homework number? 12? 12 was 2 problems. Did you figure out that hint that I gave you? Because I don't know who wrote those questions in the textbook, but sometimes they're a little hard to interpret. I just thought maybe a little nudge would help you to understand that the formula they provided was so that you could find the starting depth with the method that you were supposed to apply, direct step method. So the next thing on your plate, of course, is the project, which is due on Monday. And our class on Friday of this week is just going to be a recorded lecture where I go over a second example related to the standard step method. So today we're going to start talking about another technique that's used for predicting gradually varied flow. We'll go through one example. And I'm hoping that we'll have some leftover time that we can actually walk over to the lab and look at the flume for a few minutes. And then the recorded lecture for Friday's class is just going to be another standard step method example. And what I hope you're doing on Friday is hanging out at the lake, relaxing, getting sunburned, cheering the canoes, that kind of stuff. So,
doing the hydraulics project?
No. You've already got the hydraulics project done. Don't use that as an excuse to skip the day at the lake. Yeah. Do we have any more homeworks? I think there is one more homework. Let's look at the schedule. There it is, schedule. So there is a homework 13 that you'll submit next Friday. So our last class meeting of the semester is next Friday. We're really in the home stretch now. Of course, our final exam is the last final exam of the entire finals week. So Friday afternoon.
Gives me the most time to study.
Most time to study, most time to just savor the feeling before summer begins. Yeah. All right. Any other announcement or schedule type questions before we review the direct step method and begin on this standard step method example? Okay. Now, remember, the wide channel is one which is at least 20 times wider than it is deep. And when we have a wide channel, it's a little bit easier than usual for us to find the normal depth, because what we're doing is we're excluding the resistance that occurs at the edges of the channel, and we say that it's just the bottom width that applies wetted perimeter. So that simplifies the geometry when we have a wide channel. And so Manning's equation simplifies down to this formula for calculating the normal depth in terms of the flow per unit width, Manning's roughness N, and the channel slope. Now, sometimes when we are applying gradually varied flow equations, we need to know what is the slope of the energy grade line. And so we can rearrange this formula to solve for a slope. Now, the slope that we're solving for isn't necessarily the channel slope. We're saying it's the slope of the energy grade line at a certain point if we put in the depth at that point. So we're kind of, I wouldn't say misusing Manning's equation, but we're using it in a different way than it's most of the time applied. Most of the time we're applying Manning's equation to say what is the normal depth for steady uniform flow where you've got a certain channel slope. But we can also use that same equation to solve for the slope of the energy grade line if the depth that we're putting in is the actual flow depth at a certain location. So like where we break this channel up into segments, remember, part of what we had to do is find out what's the slope of the energy grade line at location 7, at location 6, and then the average of the two. So we're trying to find out what's the slope of the energy grade line at the midpoint. And sometimes if we've got a wide channel, it becomes even easier to do that with this simplification of how you're solving for slope. So I just wanted to point out that application of the wide channel assumption. And then remember, our definition of specific energy is simply depth plus some expression of velocity head, whether it's v squared divided by 2g, q squared divided by 2ga squared, or the velocity head in terms of flow per unit width. Now, here's a review of what we saw from the example last time. We use this direct step method when we're trying to predict either the length of the backwater curve. So in the example and in the homework, I think what you were solving for was some unknown length, L. But if you were given L, you could find out what is the depth, some known distance upstream. So if I told you, for example, the depth upstream of a sill is 3 meters, how far upstream? Maybe I'm interested in 200 meters upstream. So I tell you, L is 200 meters. You know the downstream depth. Find the upstream depth. You could also use the direct step method for that if the channel is rectangular. There's a big limitation with the direct step method, and that is it assumes that the channel geometry remains constant. It really can't handle what happens if the channel gets wider or narrower between 2 points. And it can't really handle what happens if it goes from rectangular to trapezoidal. Or, like in the real world, channels aren't necessarily prismatic at all. They're irregular in shape. You know, if you've ever driven alongside a creek, you can see that the creek maybe is collapsing in on itself at one property. Another property, they've lined up rocks and bricks and tires to try and prevent some kind of erosion of the channel. So the geometry is really irregular. And the direct step method doesn't have much applicability to any channel except for a channel which geometry is remaining constant. So we can go through the process of finding the specific energy at each of the cross sections and at the midpoint, and then using that to relate the distance between points where there's a certain amount of specific energy changing. So the delta E that it's talking about is the difference between, you know, here at 6 and 7, the depth plus the velocity head minus the depth plus the velocity head. So that's the delta E between 2 segments. And then the slope, S naught, that's the slope of the channel. So that's constant. But then what would be changing in each of these segments is the slope of the energy grade line at the midpoint. So this really only applies if you've got a rectangular channel that is staying rectangular all the way up through the backwater curve. So this isn't applied very easily when the channel geometry changes. So the standard step method is the solution to that. So last time when we're doing the direct step method, we're only applying it really for trapezoidal or rectangular channels. But the standard step method can be used regardless of the shape of the cross section. And I've got to warn you here, this little siren, it's not really a siren, the light, it's a warning that 1 and 2 mean different things than they've meant before. Because in all of the formulas I've showed you so far, whether it was closed channel or open channel, 1 has meant upstream and 2 has meant downstream. But in the context of just the standard step method, what we mean by 1 is the location where we know the depth, and location 2 is where we don't know the depth. So it doesn't mean upstream, downstream in the standard step method. So keep that in mind. We'll talk about this equation here, and it applies to this figure where we've got some datum, an elevation datum, this lowest line. We're measuring all of our elevations, regardless whether they're upstream or downstream, against this datum. So it could be sea level, for example. And so the distance from the datum up to the bottom of the channel is Z. So you'll see that Z1 would be the distance from the datum to the bottom of the channel here at location 1. And of course, water depth is described as Y. And there's some velocity head, which is the distance from the water surface up to the energy grade line. Now, there's a new term we haven't seen before, and they're designating this WS, which means water surface. And water surface is simply the elevation of the water surface above the datum. So if you add together Z and Y, that's what we mean by water surface. So water surface elevation. This formula says that if you have a location 1, which is where you know the depth, and presumably you know the velocity head, and you know the elevation of the channel above the datum, so we know everything that we need to know at location 1, what we're trying to predict is how deep is the water some distance away. Now, if you've got subcritical flow, the way that you apply the standard step method is you work downstream. So you work, location 1 is downstream, and you're working in the direction of the unknown, which is the depth upstream. In the case of supercritical flow, it's the reverse of that. You would apply, in supercritical flow, you'd apply the method in the downstream direction. So you'd start off with some known depth, and your unknown you're predicting would be downstream from that. So if you look at what's on the left-hand side of the equation, in this, what the figure is pictured here, this is subcritical flow that's pictured, because we know the depth at location 1, and that is the downstream depth. And so we know WS1, so we know, maybe we've measured it with some sort of a gauging station. There are, in West Virginia, about between 100 and 120 locations where they've got stream gauges that are continuously monitored across the entire state. And that's not very many. If you think about how many rivers and creeks and streams we've got, that in all of those rivers, there's only about 100 to at most like 150, even if you include those that are monitored non-continuously but on a daily basis. There's not very many locations where we have physical measurements of the water depth. And so these methods can be used to extrapolate what will be the depth of the water some distance upstream or downstream from the location where it's physically measured. So for example, if we have a river gauge here in Huntington, which we do, then they could use that gauge to say what is going to be the depth of the water 10 miles upstream. Like, what's the name of that hunting area that's along Route 2? Green Bottom. Yeah. So they don't have a gauge at Green Bottom, but when the water levels are high, that entire area can be underwater. And the way that they predict whether it's going to be underwater is by knowing the conditions at a gauge that's in the vicinity, but not at every location where we're interested in the depth will we have physical measurements. Okay, so at location 1, we know the water surface, we know the velocity head, and now the head loss that this is talking about is simply the difference between the energy grade line and if we had the upstream location, a horizontal line. So this top line here that's dashed is a horizontal line where it's the total amount of energy that there was upstream. So the head loss is the difference in energy between the upstream location and downstream. And the upstream location where we don't know the depth, what we're trying to predict is the water surface. So WS2 is the unknown. So we're in a problem that we've been in before where we've got too many unknowns. Do you remember there have been several problems this semester where we had too many unknowns, and so we basically just made a guess. And we said, well, you know, we'll start with a guess and then we'll see how do things work out with that guess. And if it doesn't work out perfectly, then we'll change our guess and try and get closer to the solution by iteration and making adjustments. That's what we're going to do in the standard step method. Is this approach that's built in the spreadsheet I'm going to show you in a minute is you're going to assume some water surface elevation at location 2, which is where you're trying to predict it. And sometimes your guess can be guided by what kind of a water surface profile you have. Do you remember that we talked about M1, M2, M3, those kinds of profiles? Well, those kinds of profiles can tell you if the water is getting deeper or shallower as you go upstream or downstream. So for example, if our unknown is here on the downstream end of a mild slope, and we calculated the normal depth, we calculated the critical depth, and we have a measured depth that's above both of them, then from that we know we're in the M1 zone. So we know as you work upstream, the depth is decreasing for an M1 profile. So that's kind of depicted here. It's deep downstream, upstream, it's shallower. So we could guess, if we go back to this method, we don't necessarily know the value of the water surface upstream, but we can have an informed guess. Like we know whether we should make it deeper or shallower than the location here where we do know the depth. So Start with an educated guess. And now, based on that guess, you're going to find out how much head loss would there have to be if that is the water surface depth. And so you'd calculate the difference in specific energy between the 2 points, and we're going to call that the observed head loss. Now it's just an if kind of a guess. If the water surface is at a certain elevation, how much head loss would correspond to that? And now we're going to compare it to what we call a calculated head loss. And the calculated head loss is based on the slope of the energy grade line, S sub F, at the midpoint between the two, the upstream and the downstream location, times the length between them, and then some coefficient that relates to the difference in velocity head between the 2 points. So we'll go through this process, and I think the procedure will make more sense when you see it in the spreadsheet. But we're going to be comparing the 2 head losses together, and if they don't match, then that tells us that our guess of the water surface wasn't accurate, because the head loss should be the same, observed and calculated, if you've got the correct water surface. And so if they don't match, then you'll estimate a new calculated water surface elevation with an update kind of technique that takes into account the velocity at 2, kind of an adjustment. We'll use this formula to calculate the adjusted water surface elevation, and then we'll split the difference between our initial guess and our new guess. And this is how we can ultimately achieve convergence, is by incrementally getting closer and closer to some guess that makes the observed and the calculated head loss match up. How many people in here work at the Army Corps of Engineers? So, I mean, about a third of the class works at the Army Corps. How many of you have heard of HECRAS? Few people? So HECRAS is kind of like one of the most important pieces of software that they run over at the Army Corps of Engineers. It's the software that they use to model rivers. And HECRAS is using this in the background. The technique that you're going to learn how to solve with the spreadsheet has been automated so that they can have really lengthy rivers with changing cross sections and all of the calculations that you need to go through. We're just going to do it for 2 points, and you'll see it's kind of an involved process for just 2 points. The HECRAS software can be applied for hundreds of miles of river, and it's really stable and well developed and important software, but it's also important to know how it works in the background. So we're going to go through this process of starting with a guess and cyclically recomputing until we achieve convergence. Okay, so this is the example that we're going to work, and I mentioned that there's a template file available on Blackboard right now. It's called Standard Step Method. That's the file you should download. Now remember, location 1 is where we know things. So what we know is that a certain location, the water depth is 5 feet, and you'll notice invert here. That means the elevation of the bottom of the channel is at 5 feet at location 1. And so that means the distance from the bottom of the channel to the datum is 5 feet. The channel's 25 feet wide with a 2-to-1 side slope. Upstream, 1,000 feet, this is transitioning to a rectangular channel. So it still has a bottom width of 25 feet, but basically what's happening is that these side slopes are gradually folding in. So the side slopes, as you move upstream, are coming upward until it's vertical. And upstream, the invert is 7 feet. And so from that we can know the channel slope, because it's 1,000 feet between them and 2 feet of elevation. So that's how we're going to know what is the slope of the channel. So we've got 1,000 cubic feet per second going through that. The N value here is referring to the roughness of the material. So maybe it's some sort of a grass-lined channel that has a roughness of 0.05. And then the expansion coefficient, 0.03, that's what we are going to use here as the C value in the calculated head loss. So that's just simply related to the fact that when the geometry of the channel is changing, it's kind of like a local loss that applies to the energy that's dissipated when a channel is changing shape. So it's the C value we're going to use in that formula. So that's kind of the process. What we want to know is how deep is the water if you go 1,000 feet upstream. So we know what the channel looks like, and it was 5 feet when it was rectangular, but if you move 1,000 feet upstream, how deep is the water there? Okay, so here's the template that we're going to start with. We've got the channel geometry there just to remind us, and some of these formulas that we're going to use along the way just so that they're handy. And let's fill in some of the preliminaries that we already know. For instance, we know the flow rate Q is 1,000 CFS, and the given N value is 0.05. Okay, Z1 is simply the distance from the datum to the bottom of the channel at location 1. So here it told us the invert is 5 feet. That means Z equals 5 at 1. And here, this sketch is telling us the invert is 7 feet at location 2. So Z2 is 7. The given expansion contraction coefficient C value is 0.3. And then the length of the section that we're trying to figure out, it's 1,000 feet upstream from section 1 to section 2. So L is 1,000 feet. Okay. Now, here at the known section, the values are going to be the same. And you'll notice there's lots of different rows here. Each row represents a different guess. This is different from the method that we worked in class on Monday, where each row represented a different segment. Here we're doing it just in a single jump. We're jumping from location 1 to location 2 in a single step, and each row is going to represent a different guess. So I wanted to differentiate between that. And at the known section, regardless of how many guesses we do, the data is going to stay the same, because it's already known to be 5 feet. So here for the depth, y1 equals 5. The area, if we've got a trapezoid like this, okay, so the area is going to be 5 feet times 25. So 5 times 25 plus, so if it's 5 feet deep on this side triangle, and a 2-to-1 side slopes, then that means it's 10 feet across the top. So then it would be plus 5 times 10. So the area is 175 square feet. Okay, so V equals Q divided by A. So Q divided by the area. Okay. Wetted perimeter, we've got to have the 25 feet across the bottom plus 2 times this side distance. And so it is 25 plus 2 times, okay, so it's going to be the square root of 5 squared plus 10 squared to get that side length. So square root of 5 squared plus 10 squared. .361 is the wetted perimeter for that trapezoidal channel. Okay, hydraulic radius equals area divided by wetted perimeter. Okay, energy we're going to define as the elevation of the datum from the datum to the bottom of the channel, so that's Z, plus Y at that location, plus the velocity head, V squared divided by 2G. Okay, so equals Z1 plus the depth plus the velocity head. So V squared divided by 2 times G. We're working in traditional units, so that's 32.2. I think the example from Friday's class is SI units, if I remember correctly. So Always be sure to adjust G accordingly if you've swapped units around. Okay, so we've got 10.507 feet of head at location 1, and then the slope of the energy grade line at 1, we're going to use this formula. This is Manning's equation with, in traditional units, the 1.49 units conversion factor that applies. So solving, and of course this is not a wide channel. Yeah, it's not wide. It's not wide enough to be considered wide. So we're going to use the full version of the Manning's equation to find the slope of the energy grade line. So it is equal to the n value multiplied by q divided by 1.49 times the area times the hydraulic radius to the power of 0.66667. And then close the parentheses. How many? Kind of losing track there. I think I need 2. Yep. And then all of that is squared. So used Manning's equation, and we get the slope of the energy grade line should be 0.00644. And once I've calculated it for one row, I'm just going to drag this down. It's going to be the same for all of them. Well, I need to change this. It started counting upwards with the depth. But, oops, it's always 5. The depth stays at 5 feet. We may need additional rows, and if we do, we can just keep dragging it downward. All right, so what step are we at so far in this? Well, we've basically just calculated E1. So what we're going to have to do now is assume some water surface for location 2. So let's guess how deep the water is, and then from that we'll calculate the water surface at 2. What if the water depth is a little bit deeper? So let's just say 5.1 feet. I don't know how much deeper it's going to be upstream, but let's start with a little bit deeper, 5.1 feet. Okay, so water surface at 2, by definition, water surface is Z2. I'm going to anchor the reference there, and this is important because each subsequent row is going to be different, but I always want it to look up here to Z2 for the first part of what is the water surface, plus the depth at 2. Okay, so the water surface is the distance from the datum up to the water, and if our depth is 5.1, then the water surface depth is 12.1. Luckily, the geometry here is relatively easy because it's rectangular. So area, for example, is simply 25 feet wide times whatever the depth is. That's easy enough for the cross-sectional area. Velocity is likewise pretty straightforward. It's just Q divided by A. So equals Q, anchor the reference there, divided by the area. So this is what the velocity would be if the depth is 5.1. Wetted perimeter, again, simple because it's rectangular. It's just going to be the bottom width of 25 plus 2 times the depth for a rectangular channel. So 25 plus the left depth and the right depth. So 2 times whatever the depth is gives us the wetted perimeter. Hydraulic radius is the area divided by the wetted perimeter. Okay, E is the water surface plus the velocity head. Or we could add Z plus Y plus the velocity head. Since I've already got the water surface, let me just do that. So equals water surface plus the velocity head, V squared divided by 2 times 32.2. Okay, so let me pause for a second. Is there anybody who needs to see a certain cell formula, or is there something that I went through too quickly that I could circle back to a second time? We know E1 and we know E2 if this is the depth. So back in our procedure here, we know E1, we know E2. So from that, we can calculate this observed head loss. Before we do, let's just calculate what is the slope of the energy grade line at 2, because we're going to want to know the slope of the energy grade line in the middle, between 1 and 2. So again, we're going to use this formula, rearranging Manning's equation to solve for the slope of the energy grade line. So it is n with an anchoring to the reference times q anchoring the reference divided by 1.49 times the area times the hydraulic radius, and all that should be to the power of 0.6667, and then close parentheses twice to the power of 2. So just applying the same formula that we had used here. I'm doing it again for the second segment because at some point I want to know S sub f bar, the slope of the energy grade line at the middle between the 2 points. I'm going to use that later. So let me just calculate it now. 0.01245. Okay, so the observed head loss, here's the formula for the observed head loss. Observed head loss equals E2 minus E1. All right. And now S sub f bar is just going to be the average of the S sub f at location 1 and the S sub f at location 2. So it is this one plus that one divided by 2. Our book does a lot of things really well, but it kind of astonishes me, like these complex step-by-step procedures. It surprises me that they don't provide templates like that the textbook author doesn't. They kind of just expect that people would do this by hand. And I think I did it by hand one semester, and I thought, we got to get this into a spreadsheet, because as many times as we're going to have to iterate, it just is page after page of tedium. So as bad as it is to set this up on a spreadsheet, I mean, once we get the first row of things entered, we're just really going to be dragging downward for most of these calculations. And so we're really fortunate to have these tools where a lot of engineers in past years would have had to try and do this by hand. Okay, so now we've got the observed head loss. Let's try and calculate the calculated head loss, H sub L calculated. All right. Makes me wish that I'd added a special column just for the velocity head, because then we could just click on the column of velocity head. I mean, I guess I might as well. Let's modify this. Let's create a velocity head column for both 1 and 2. So I'm putting it next here to the velocity. Okay, so this is, I'll just call it V1 head, meaning it's going to be V squared divided by 2G. So V squared divided by 2 divided by 32.2. V2 head. So it is velocity squared divided by 2 divided by 32.2. All right, so now it's going to make this just a little bit easier, because we don't have to embed calculating the velocity head into the equation. We can click on the locations. Okay, so it is equals to the average slope of the energy grade line, which we just barely calculated, times the length, the distance between these 2 points, which is 1,000 feet, anchoring the reference there, plus the C value, 0.03, anchor that reference, and then times the absolute value of the velocity head at 2 minus the velocity head at 1. If we hadn't calculated velocity head as an extra standalone column, then we would have had to type the velocity head formula in there. And I mean, we could do it. It would just maybe be unnecessarily complex to embed it inside the absolute value. So this is saying that the calculated head loss is 9.579 feet. So observed and calculated don't match. So what that means is this actually isn't the depth. It's not actually 5.1 feet upstream. We're going to have a new guess. Rather than just picking one at random, we can kind of automate and guide the optimization and iteration process by calculating a new calculated water surface elevation for 2. Okay, so this next column is going to use this formula here. So what we're calling the calculated water surface at 2 is the water surface at 1. Okay, now we didn't calculate a column that says water surface at 1, but do you remember that water surface means depth, so y1 plus z1. Okay, so water surface at 1 is y1 plus z1. And I need to anchor the reference to z1 since it's up here in these constants. Okay, so that's y1. I'm sorry, water surface at 1. Plus the velocity head at 1. Well, we do have that, luckily, a column that we can just click on. So here's the velocity head at 1. Plus the calculated head loss. So that's what's in cell V30. I can't click on it because my formula is in the way, but I can just type V30 minus the velocity head at 2. So here's the velocity head at 2. Okay, so this is saying that the calculated water surface depth should be 19.3. Now the updated is going to be this previous water surface depth plus the calculated water surface depth. And the previous one was 12.1, and the new one that we're calculating is 19.3. So we want to split the difference between those, so the average. So it is the previous plus the new divided by 2. Okay, so it says for the next iteration you should use 15.62. Now there's this column here that's percent difference that we're going to use as an indicator for whether the solution is converged. So for this percent difference, it's going to be the new, let's do the updated water surface minus the original one. Put parentheses around that. Divided by the updated times 100. So what this means is we're looking for the percent difference to go down to below 1%, suggesting that the water surface elevation isn't changing anymore within each row. Okay, so for this water surface, we're going to set it equal to the previously adjusted value from the last row.
Can you do the percent difference again? Can you show it real quick?
Yep, I can. Absolutely. It is equals parentheses the new value minus the old value divided by the new value and times 100.
All right, thank you.
Yep. Okay, so now it didn't match. We've got a bad guess, and we want to do better. So our new guess equals this updated value. So we know the water surface, and the depth is going to be this water surface minus the 7-foot z difference between the water surface and the depth. So the water depth, y1, equals the water surface minus z2. So if the water surface is 15.62, then the new depth would be 8.62. Now, I think this is where the beauty of automation kind of takes off for us. We can just select all of this and drag down. And so let's look at what it did. So we said set the new guess based on the output of the last iteration. So if the water is 8.62 feet, then we got a new area, a new velocity head, wetted perimeter, energy, slope of the energy grade line. The observed and the calculated head loss are much closer this time. So that's an improvement. And so the percent difference between the in and the out is negative 2.6. And that's okay that it's negative. That doesn't mean anything bad. So what we can do is all of it now, the entire row, because really the main thing that should be changing is referring to the previous updated water surface depth for the next row. So if I drag this down, then instead of looking here at the next one, when I drag this down, it's going to be looking at this one, that's what I want it to do. So if you calculate everything for the next row, we're down below 1%, but the observed and the calculated head loss, we could do better. If you look at the depths, it says it's 8.22 feet. The last one was 8.62. I think it's good for us to continue iterating until the depth is no longer changing. Even if the percent difference is less than 1, let's aim higher. 8.06. Okay, I'm going to have to take these constants down a bit further. I want to make sure that it thinks it should start counting upwards for the depth. So all of these need to stay the same. All right, drag that all the way down. It certainly converges. You know, the depth 8.06, 8.05, 8.05, 8.05. So this is the correct depth. The water upstream, where it had moved to a rectangular channel, the water depth is 8.05 feet. So we went through a process of just guessing some value, and it kind of self-corrected and adjusted the guesses in subsequent iterations until the solution converged. And the final answer is the water depth at location 2, where the channel is rectangular, is 8.05 feet. Okay, so that is our final answer. And that's the standard step method. So things are different if you've got supercritical flow, and things are different if you've got SI units instead of traditional units. So we're going to look at some of those differences in the example that's going to be recorded for Friday's class. It's 1:46. Unfortunately, I don't think we have time to go into the lab today to look at the flume, but I do want to try and squeeze that in because I think there's a lot we can learn just by looking at different flow states in the flume. So we'll try and do that sometime next week. Remember that for our class this week, though, on Friday, the lecture's recorded because hopefully you'll be participating in some way for the Virginia's conference. And then we'll be back together in person on Monday, which is the same day that you're turning in your project. If you've got any questions on the project, you can email me, call me on Teams, stop by my office. I'd be glad to help you in any way that I can.